Welcome to the fascinating world of modern physics. In this video, we'll embark on a journey through the revolutionary ideas that have shaped our understanding of the universe over the past century. From the mysterious quantum realm to the vastness of relativity, modern physics challenges our intuition and opens up new possibilities for technology and discovery. Let's begin by exploring what sets modern physics apart from classical physics and why these breakthroughs continue to inspire scientists and thinkers around the globe. For the 20th century, classical physics, rooted in Newton's laws and Maxwell's equations, explained most natural phenomena. However, as scientists probed deeper, they encountered puzzles that classical theories couldn't solve. Enter modern physics, which introduced concepts like relativity and quantum mechanics. These new ideas revolutionized our understanding of matter, energy, space, and time. In this scene, we'll compare the key differences between classical and modern physics, setting the stage for the groundbreaking discoveries ahead. The dawn of the 20th century, physicists faced a crisis. Classical theories couldn't explain phenomena like blackbody radiation or the photoelectric effect. Max Planck and Albert Einstein proposed that energy comes in discrete packets, or quanta, laying the foundation for quantum mechanics. This radical idea challenged the notion of continuous energy and set the stage for a new era in physics. Quantum mechanics would soon reveal a world where particles behave like waves and uncertainty reign. Quantum mechanics didn't just solve old mysteries, it introduced new ones. Concepts like wave-particle duality, uncertainty, and superposition defied common sense. Physicists like Niels Bohr and Werner Heisenberg developed mathematical frameworks to describe the strange world. Their work led to the famous uncertainty principle and the realization that at the smallest scales, nature is fundamentally probabilistic. The quantum revolution continues to challenge our understanding of reality. Quantum mechanics explored the very small. Albert Einstein's theory of relativity transformed our view of the very large. Special relativity showed that space and time are intertwined, and that the speed of light is the ultimate speed limit. General relativity went further, describing gravity as the curvature of spacetime itself. These theories have been confirmed by countless experiments and have profound implications for everything from GPS satellites to black holes. Special relativity, published by Einstein in 1905, introduced two key ideas. The laws of physics are the same for all observers in uniform motion, and the speed of light is constant for everyone. This led to mind-bending consequences like time dilation and length contraction. For example, as objects move faster, time slows down for them relative to stationary observers. These effects, though tiny at everyday speeds, become significant near the speed of light. Einstein's general relativity, published in 1915, redefined gravity. Instead of a force between masses, gravity became the result of massive objects curving the fabric of spacetime. This theory predicted phenomena like the bending of light by gravity and the existence of black holes. General relativity has passed every experimental test so far, and its predictions are essential for technologies like GPS, which must account for time differences caused by Earth's gravity. One of the first triumphs of quantum theory was explaining the photoelectric effect. When light shines on certain metals, it can eject electrons. Classical physics couldn't explain why only light above a certain frequency worked. Einstein proposed that light is made of particles or photons, each carrying a quantum of energy. This discovery not only confirmed the quantum nature of light but also earned Einstein the Nobel Prize. One of the strangest ideas in modern physics is wave-particle duality. Experiments like the double-slit experiment showed that particles such as electrons can behave both as particles and as waves, depending on how they are observed. This duality is at the heart of quantum mechanics and challenges our everyday understanding of matter and energy. It's a reminder that the quantum world operates by rules very different from our own. Werner Heisenberg's uncertainty principle states that it's impossible to know both the exact position and momentum of a particle at the same time. The more precisely we know one, the less precisely we can know the other. This isn't just a limitation of measurement, it's a fundamental property of nature. The uncertainty principle has profound implications for everything from atomic structure to the limits of scientific knowledge. Quantum superposition is the idea that particles can exist in multiple states at once until they are measured. For example, an electron can be in two places at the same time, or a photon can take multiple paths. This concept is famously illustrated by Schrödinger's cat, a thought experiment where a cat is both alive and dead until observed. Superposition is essential for technologies like quantum computing. Quantum entanglement is a phenomenon where two or more particles become linked, so that the state of one instantly influences the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, has been confirmed by experiments and is a key resource for quantum communication and cryptography. Entanglement challenges our ideas about locality and causality. Standard model is the framework that describes the fundamental particles and forces except gravity in the universe. It includes quarks, leptons, and first-carrying particles like photons and gluons. The discovery of the Higgs boson in 2012 confirmed a key part of the model. While the standard model has been incredibly successful, it leaves many questions unanswered, such as the nature of dark matter and gravity. Study the smallest building blocks of matter. Physicists use particle accelerators. These massive machines, like the Large Hadron Collider, smash particles together at near-light speeds, revealing new particles and testing the limits of the standard model. Particle accelerators have led to discoveries like the Higgs boson and have applications in medicine and industry. They are essential tools for modern physics research. Quantum field theory, QFT, combines quantum mechanics and special relativity to describe how particles interact through fields. In QFT, particles are seen as excitations in underlying fields that fill all of space. This approach has led to incredibly accurate predictions and is the foundation for the standard model. QFT is a complex but powerful framework that continues to drive new discoveries in physics. For every particle, there exists an antiparticle with opposite charge. When matter and antimatter meet, they annihilate, releasing energy. This symmetry is a fundamental aspect of modern physics, but it also raises questions. Why is there more matter than antimatter in the universe? Experiments with antimatter help physicists probe the laws of nature and search for new physics beyond the standard model. Quantum tunneling is a phenomenon where particles can pass through barriers that would be impossible according to classical physics. This effect is crucial for processes like nuclear fusion in stars and is the basis for technologies such as tunnel diodes and scanning tunneling microscopes. Quantum tunneling shows how the rules of the quantum world can lead to surprising and useful effects. Quantum computing harnesses the principles of superposition and entanglement to perform calculations far beyond the reach of classical computers. Quantum bits or qubits can represent multiple states simultaneously, allowing quantum computers to solve certain problems much faster. While still in its early stages, quantum computing promises to revolutionize fields like cryptography, optimization, and materials science. Lasers are a direct application of quantum mechanics. By stimulating atoms to emit light in a controlled way, lasers produce highly focused and coherent beams. Quantum optics explores how light interacts with matter at the quantum level, leading to technologies like fiber optic communication, holography, and quantum cryptography. These advances have transformed communication and information processing. Modern electronics rely on semiconductors, materials whose electrical properties can be precisely controlled. Quantum mechanics explains how electrons move in these materials, enabling the creation of transistors, diodes, and integrated circuits. These components are the foundation of computers, smartphones, and countless other devices. The quantum understanding of semiconductors has powered the digital revolution. Superconductivity is a phenomenon where certain materials conduct electricity with zero resistance at very low temperatures. This effect, explained by quantum mechanics, allows for powerful magnets, lossless power transmission, and advanced medical imaging devices like MRI. Research into high-temperature superconductors could revolutionize energy and transportation in the future. Nuclear physics studies the structure and behavior of atomic nuclei. It explains phenomena like radioactivity, nuclear fission, and fusion. These processes power the sun, provide energy in nuclear reactors, and have applications in medicine and industry. Understanding nuclear physics is also essential for exploring the origins of elements in the universe. Modern physics has transformed our understanding of the cosmos. Astrophysics applies the laws of physics to stars, galaxies, and the universe as a whole. Cosmology explores the origin, evolution, and fate of the universe, including the Big Bang, dark matter, and dark energy. These fields use both quantum mechanics and relativity to answer some of the biggest questions in science. One of the most important discoveries in cosmology is that the universe is expanding. Observations of distant galaxies show that they are moving away from us, implying that the universe began with a Big Bang. This expansion is described by general relativity and has led to new questions about the ultimate fate of the cosmos. The discovery of cosmic expansion has reshaped our view of the universe. Most of the universe is made of mysterious substances called dark matter and dark energy. Dark matter exerts gravity but doesn't emit light, while dark energy drives the accelerated expansion of the universe. These components make up about 95% of the cosmos, yet their true nature remains unknown. Discovering what they are is one of the biggest challenges in modern physics. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. Predicted by general relativity and confirmed by observations, black holes are laboratories for extreme physics. They challenge our understanding of space, time, and information, and may hold clues to a deeper theory that unites quantum mechanics and gravity. Gravitational waves are ripples in spacetime caused by massive accelerating objects, like merging black holes or neutron stars. First predicted by Einstein, they were directly detected in 2015, opening a new window on the universe. Gravitational wave astronomy allows us to observe cosmic events that are invisible to traditional telescopes, providing fresh insights into the most violent processes in the cosmos. One of the biggest unsolved problems in physics is how to combine quantum mechanics and general relativity into a single theory of quantum gravity. Such a theory would describe the behavior of spacetime at the smallest scales and could explain phenomena like the Big Bang and black holes. Approaches like string theory and loop quantum gravity are active areas of research, but a complete theory remains elusive. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can vibrate in different ways to produce all known particles and forces, potentially unifying gravity with quantum mechanics. While string theory is mathematically rich and elegant, it is yet to make testable predictions. It remains a leading candidate for a theory of everything. Symmetry plays a central role in modern physics. Many fundamental laws are based on symmetry principles, such as conservation of energy, momentum, and charge. Symmetry breaking can lead to new phenomena like the Higgs mechanism, which gives particles mass. Understanding symmetry helps physicists uncover the deep structure of the universe and predict new particles and forces. Higgs boson is a particle associated with the Higgs field, which gives mass to other particles. Its discovery at the Large Hadron Collider in 2012 was a major triumph for the Standard Model. The Higgs boson's properties are still being studied, and its existence raises new questions about the nature of mass and the stability of the universe. Neutrinos are nearly massless particles that rarely interact with matter, making them incredibly difficult to detect. They are produced in nuclear reactions such as those in the Sun and play a key role in the universe's evolution. Recent discoveries show that neutrinos have mass and can change type or oscillate, challenging the standard model and opening new avenues for research. Quantum measurement problem asks, how does a quantum system go from being in a superposition of states to a single outcome when measured? Different interpretations of quantum mechanics, such as the Copenhagen interpretation and many worlds theory, offer different answers. This deep question touches on the nature of reality and the limits of human knowledge. Modern physics has led to a host of new technologies. Quantum mechanics underpins lasers, MRI machines, atomic clocks, and quantum computers. These advances have transformed medicine, communication, navigation, and information processing. As research continues, we can expect even more revolutionary applications in the years ahead. Modern physics raises profound philosophical questions. What is the nature of reality? Does the universe have a beginning or end? Can we ever fully understand the quantum world? These questions have inspired debates among scientists and philosophers alike. Exploring the philosophical implications of physics deepens our appreciation for the mysteries of the universe. Advances in modern physics depend on innovative experimental techniques. From particle accelerators to space telescopes, new instruments allow scientists to probe deeper into the quantum and cosmic realms. Precision measurements and creative experiments are essential for testing theories and discovering new phenomena. The interplay between theory and experiment drives progress in physics. Mathematics is the language of modern physics. Complex equations describe everything from quantum fields to the curvature of spacetime. Mathematical models allow physicists to make precise predictions and uncover hidden patterns in nature. The deep connection between math and physics is one of the most beautiful aspects of science. Women have made vital contributions to modern physics, from Marie Curie's pioneering work on radioactivity to contemporary leaders in quantum research. Despite historical barriers, women continue to break new ground and inspire future generations. Highlighting their achievements is essential for building a more inclusive and innovative scientific community. The principles of modern physics are all around us. From the electronics in our devices to the GPS in our cars, quantum mechanics and relativity power much of modern technology. Understanding these principles helps us appreciate the hidden science in our daily lives and the ongoing impact of physics on society. Despite its successes, modern physics faces many unresolved questions. What is dark matter? How can we unify quantum mechanics and gravity? Are there extra dimensions or parallel universes? These mysteries drive ongoing research and remind us that the universe still holds many secrets waiting to be discovered. The future of modern physics is bright and full of promise. New experiments, powerful computers, and international collaborations are pushing the boundaries of knowledge. As we explore the quantum and cosmic frontiers, we may discover new laws of nature and technologies that transform our world. The adventure of discovery continues. Modern physics has a profound impact on society. Its discoveries lead to new technologies, medical advances, and a deeper understanding of our place in the universe. Physics education and outreach inspire curiosity and critical thinking, helping to build a more informed and innovative world. The benefits of physics extend far beyond the laboratory. Modern physics connects with many other fields, from chemistry and biology to engineering and computer science. Techniques developed in physics are used to study complex systems, design new materials, and solve real-world problems. This interdisciplinary approach accelerates innovation and leads to breakthroughs across science and technology. Teaching and learning modern physics can be challenging but also deeply rewarding. Visualizations, experiments, and hands-on activities help make abstract concepts more accessible. Encouraging curiosity and critical thinking prepares students to tackle the mysteries of the universe and contribute to future discoveries. As we reach the end of our journey through modern physics, it's clear that this field is full of wonder, mystery, and possibility. From the tiniest particles to the largest structures in the universe, modern physics continues to expand our horizons and inspire new generations of scientists. The quest to understand the universe is ongoing, and the discoveries yet to come may be even more astonishing than those we've seen so far.